All right. So good morning, everyone. So today I will continue talking about multi-view structure for motion. We will talk about averaging techniques, mostly averaging essential and fundamental matrices. At least half of the talk will be on work that was done here with Yoni, Amnon, and Merav. So let's remind ourselves. So we last time we talked about incremental methods and factorization methods, and we started talking about averaging techniques. The idea was to take essential matrices, factor them into rotations and translations. These give you relational measures between image I and image J. Then perform rotation averaging, find the global orientations given relational rotations, and translation averaging. These compose the algorithm LUD that we discussed, and we talked about the advantages and disadvantages. So this is just a summary from last time. And now I want to move on to the question of, given a graph, so usually a graph, view graph, contains relational measures between pairs of images, but not necessarily all pairs. And the question is, there exists a unique solution given such a graph. So obviously for some graphs, there will be a unique solution, and for some graphs, there will not be a unique solution. This question is called solvability, and in fact, to some extent, it was investigated under the name of sensor networks. And there is the concept of rigidity, graph rigidity, that we are going to discuss now. So what is solvability? Given a view graph, does it admit a unique solution, assuming the cameras are in general position? So, to answer this question, we define a sensor network to be a graph whose nodes represent the sensors, and edges are associated with relational measurements. The objective is to recover the absolute positions of the sensors. Is this clear? Let me know if you have questions. Graph rigidity is the following problem. Suppose the edges are associated with distances. Can we recover the positions of the sensor? Okay. So here is an example. Suppose the graph is a triangle, and I give you the distances on the triangle. Will it admit, can you know the positions of the absolute positions of the vertices? Of course, you can know them only up to translation, rotation, and reflection, right? So let's call those trivial transformations. Can we tell, if I tell you where the 0, 0 is, the first node is at 0, 0, etc., can you say where the other two vertices are? The answer is, of course, yes, because we know that if we know the three distances of the edges, then the triangle is determined uniquely, right? We learned that in high school, actually. Okay, what about this picture? I'd be happy to hear your answer. Is this graph, does this graph give you a unique solution if you know the distances? Anybody wants to answer?
Yes. Reflection, maybe up to reflection.
Yeah,
rotation.
Right. Again, up to rotation, translation, and reflection. Okay. So the answer is yes. Of course, the first triangle is unique. We already said that. The second triangle is also unique, and they are attached, so there is no question. What about this graph? Is it unique?
Yes, it's also unique.
Well, no.
I think no, because you can rotate the.
Exactly. I can rotate one triangle with respect to the other. Okay, so the entire structure is not rigid. Okay, each triangle is rigid, but they can rotate one with respect to the other. So that's the important thing to remember. We need the entire structure to be rigid up to these trivial transformations. What about this quadrangle? I know the distances, so.
No, it can bend, no?
What?
You can bend it, I think.
Exactly. So think about a square versus a rhombus, right? ריבוע מול מאוין. Same distances, but different shapes. Okay, you can squish it. Okay, so this is an example of graph rigidity. We actually need a different concept. Let's look at the calibrated case. So we have calibrated cameras. Okay, that means that the view graph contains essential matrices. Okay, and the question is whether the graph admits a unique global solution up to trivial transformation, rotation, translation, and reflection, assuming there is no error and that the cameras are in general position. So we need to remember those two things. So we assume that the relational measures are exact and that the cameras, for example, are non-collinear in 2D or non-coplanar in 3D. Okay, so let's look at the calibrated case. We have essential matrices between on the edges. Each of them can be factored to rotations and translation up to scale. Okay. The rotations, we have two solutions, but we can determine which of these two solutions is correct by looking at points. So we assume that we have just one unique solution for the relational rotation, Rij. Okay. Given Rij, camera orientation can be recovered, Ri, and for any connected graph, you can convince yourself that really there is no question of rigidity on the rotations. The orientations can be determined for any connected graph. Okay, you simply start with the first node to be the rotation is identity, and then you propagate the rotations. So once camera orientation is known, we know the direction between two images. Okay, so the translation is not up to scale. Okay, we know the direction, but not the scale, not the distance. Okay, solvability with known directions is called parallel rigidity. Okay, so similar to the rigidity, graph rigidity problem, we have graph parallel rigidity. Parallel rigidity is in some sense easier problem because we know the direction, but we don't know the distance. Okay, usually the direction have more degrees of freedom than the distance, right? Like in 3D, it's 2 degrees of freedom relative to 1 degree of freedom for the distance.
What do you assume about the number of cameras here?
I don't. It's the size of the graph. Okay, the number of vertices. Okay, so the question is, given a graph, and each edge is associated with an orientation, a global orientation. Okay, so you know the orientation relative to global coordinate, but you don't know the distance. The question is, does this graph admit a unique solution? This is actually an active problem in mathematics. And here is a theorem that allows you to determine rigidity. So for a graph, let's say define d minus 1e. Just I want to have a pointer. Okay, so d minus 1e is simply d minus 1 copies of the edges. Okay, and the theorem says that G, the graph G, is parallel rigid in RD if and only if there exists a non-empty set D, which is the subset of D minus 1E, with whose size, so the number of edges in D should be D times the number of vertices minus D plus 1. Okay? And that's not the only condition. The other condition is that for any subset of D, the size of the subset will be less or equal to D times the number of vertices in D0 minus D plus 1. Okay. So we will see some examples, and I think the theorem will be more clear. First, notice that in 2D, D minus 1E is simply E. Okay, D minus 1 is 1. Okay, so you ask if there is a subset of the edges whose size is 2V minus 3. Okay. In 3D, you can take each edge twice, and you say you need a subset whose size is 3 times V minus 4. And in addition, we need the condition on the subsets. Okay, so let's see some examples. Okay, sorry. Before we see examples, let me try to explain where we get this condition from. Okay, not exactly a proof, but more of an outline of the proof for the first part. Okay, so let's see. Given a vector u, we can write this expression to say that V is parallel to U. What do you see here? This matrix, which I call RU here, is a projection matrix onto the space that is orthogonal to U. Let's see that. Okay, so in this expression, in this term, okay, we take the inner product of U with V, okay, and we multiply that inner product with U. Okay, so the inner product is U transpose V and multiplied by U. Okay, and this is a normalization factor. Okay, so this matrix, this term, projects V into the direction of U. Okay. Next, so this is a projection matrix onto the subspace spanned by U. And identity minus this projection matrix will give you a projection matrix onto the space that is orthogonal to U. Is this clear?
No.
Okay, so I'm trying to write a matrix that will project a vector into the space that is orthogonal to U. So think of U as a line, okay? And I take V, which is a different line, okay? And I want to project it into this line. Let me annotate. Okay, so this is U, okay? And this is V. Okay, how do we project V onto U? I take the inner product of, so the inner product will give you the distance here. So this will be the inner product. And you need to take that distance and multiply by U. Okay, that will give you the projection of V onto U. And this is exactly what this part does. So you take U transpose, multiply by V, that gives you this distance. Okay, and then you multiply it again by U, and so it gives you a vector of this size in the direction of U. Okay, so ignore the, so I'm thinking now of U and V as a unit vector. So this normalization is comes just to account for the fact that U and V may not be normal vectors. Okay, but think about this part. Okay, so overall, this matrix is a projection of V onto U. Okay, and now if I take this matrix and instead of just using it, I'm taking the identity minus this matrix, that will give you, that will project V onto this space. Okay, so in 2D, that would be the orthogonal space is a vector that is orthogonal to U. And this would give you the projection here. Okay, so I project V to become this vector. Okay, is this clear?
Yes.
Okay. Clear? Okay. Fine. So we have this expression, RU times V equals 0. And notice that RU is a D by D matrix. Okay, so 2 by 2 in R2. Okay, so you see that it's produced by the outer product of U and U transpose. So its size is D by D. Okay, fine. Come on. Okay. Sorry, PowerPoint sometimes doesn't recover well from annotation. Okay, so now let's consider what we call a point formation. So these are endpoints, okay, P1 to Pn, and there is a graph G, such that each node represents the unknown point position Pi, and an edge Ij represents a measured direction Pj minus Pi. Okay, this is what we call a point formation. Okay, now what we ask is what formations Q1 to Qn are parallel to P1 to Pn. Okay, so given P1 to Pn in the graph, we want to know which set of points Q1 to Qn are parallel. Okay, okay. So clearly, using this equation that I showed you before, for every edge in E, what I need to write is the projection matrix R Pj minus Pi, which is composed as we did here, times Qj minus Qi equals 0. Clear? Is it clear? Okay. So we simply write this equation for every edge Pj minus Pi. Okay. Next, what we do is we take these equations. So again, we go back. We take these equations and write them in a matrix, one matrix for all the edges. Okay, so we combine them into an equation system. Okay, we call this matrix Rp. It contains all the Rpj minus Pi. Okay, and if we multiply them by this vector, which contains all the points, Q1 to Qn, we get 0.
Can you explain again why we do the subtraction between Pj and Py?
Can you say it again? I didn't hear well.
Why do you do the subtraction between Pj and Pi?
Okay, because I want to represent everything in the terms of the positions of the points. So Pj minus Pi is the relational measure that I have on the edge, right?
So you fix a j and you run it on the I?
No, for every j and I that are in the edge set. Okay, for every 2 points, if there is an edge, I will supposed to get this pj minus pi. For now, this is just a proof. This is not how I actually do it. Okay, so bear with me. Okay, but think about, you have this. You have the graph. The nodes represent P1 to Pn, and the edges represent Pj minus Pi for every pair of nodes. Okay? So this term, this equation, in this equation, Rp contains all the Rpj minus Pi for E, and the vector are all the points Q1 to Qn, and if Q1 to Qn are indeed parallel to P1 to Pn, then this equation, this product is 0. Okay. Now we can look at Rp. Let's see what size Rp has. Okay. So the vector Q1 to Qn, each point here is d-dimensional. Okay. For example, it's in R2 or R3. Okay, so the size of this vector is d times the size of the number of nodes. Okay, so this means that Rp has d times the number of nodes columns, right? Okay, how many rows do we have? For that, we need to ask how many equations we have. Okay, so we have E, the absolute value here, or the size of E, that's the number of edges. Okay, each edge gives you d equations. Why d equations? Because if we go back again, we said that the size of this matrix, the projection matrix, is d by d. Okay, so it means that each edge gives you d equations. Okay. So overall, the size of Rp is d times E. That's the number of rows, and d times V, that's the number of columns. Okay? Okay. So this is an expression for what point conformations or what sets of points are parallel to P1 to Pn. Okay. Now the last step is the following. We want to see what is the trivial null space of Rp. The trivial null space are all the translation and the scale or reflections of the points. Okay, here we don't have rotations because we know the absolute orientation of every edge. We just don't know the scale, the distance. Okay, so let's see what is the null space, the trivial null space of this equation. Okay, so obviously P1 to Pn satisfy this equation, right? Because P1 to Pn are parallel to P1 to Pn, right? That's trivial. Okay, parallel in the sense that if I try to project Pj minus Pi onto Pj minus Pi, I get 0. Okay, so this vector is in the trivial null space. Scaling will just be equivalent to scaling this vector. Okay. In addition, we need to account for translations. So for translation, think of taking P1 to Pn and changing the x value, the first coordinate, by adding 1 or by adding 2 or by adding 3. This you can write as this vector. Okay, so for every point here, I put 1, 0, 0, then 1, 0, 0, then 1, 0, 0, etc. Multiply that by T1, that would give you T in the direction of the first coordinate for all points. Okay, And similarly for the second coordinate, and here for the last coordinate. So so overall, I have D vectors that span the translations. Okay, so this was a little bit maybe fast. I want to make sure that you understand. Okay.
Here D is 3, right?
So here here D is 3. Okay, in this example. Okay, but basically I put D vectors like this.
And the S of P1 to Pn is?
So this is just the scaling of the points. Okay, if S is 1, I get P1 to Pn, and obviously those are parallel trivially to P1 to Pn. If I put S equals 2, I basically increase the size. I scale all the points by 2. And of course, all the directions will be parallel. Okay, so this is the null space, the trivial null space of RP, okay, which contains translations and scale. Okay, the number of vectors here, or the dimension of this null space, is D plus 1. We have dimension D for translations and 1 for scale. Okay, good. So overall, we got an equation system with a matrix DE by DV with a trivial null space of size D plus 1. Okay, so consequently, we can say that P is parallel rigid, which means that it only has the null space is the trivial null space, if and only if the rank RP of the matrix RP is DV. Okay, dv, we'll explain it in a minute, minus d plus 1. So dv will be the number of columns. Of course, v is less than e, right? We assume that the graph is at least connected. Okay, so dv is less than e, v is less than e. So the maximal rank of a matrix of this size is d times v. Okay, but we know that the trivial null space is always true. So we subtract that. So dv minus d plus 1. And if we don't have anything more in the null space, that means that there are nothing but the trivial transformations give you parallel conformations. Okay? So this is basically how you prove that you need to find a subset in your graph that have this number of edges, or this number of members.
You assume a connectivity, or just that the size of E is larger than the size of V?
Yeah,
because it's not equal. Like you can think of a graph of two nodes with one edge.
We will see some examples. We will see some examples. If the graph is not connected, then trivially that would be, it will be non-rigid, right? Because if it's not connected, you can take each connection, each connected component, and place it in any place you want. And so the entire graph is not rigid. Okay, so there is no assumption here, really. Okay. Okay, so just to complete this, what I showed you is that for a specific given point P1 to Pn, okay, and the graph, I can tell you that the rank of Rp must satisfy this equation in order for this to be a parallel rigid. But what we want really is to say, given a generic graph, we don't know, we don't have P1 to Pn, okay? We want to know if the graph is parallel rigid, okay? So we can know the rank of Rp only for specific measurements. Okay. Because of this, the theorem that I showed you before, which applies generically to any graph without specific point formations, that's why we need the second condition, which told you that also subgraphs, subsets satisfy this constraint, if you remember. Let me go back, just to remind you. Okay, we said that we have a non-empty set that satisfy this part. That's what we showed. And all subsets will satisfy this condition. Okay, so you need that because you want to be generically true for any point formation that correspond to this graph. Okay, let's see some examples. And let's get back to this, to the rest of this. It's probably better to see some examples before I continue on this. Okay, so let's start. This triangle. So think about the following thing. Every edge here, you know the direction. So you know that this is, for example, vertical, this is diagonal, and this is in this direction. Okay? Is this triangle determined? Are the position determined? Up to what? Notice. Up to translation and scale. Okay? And uniform scale. What do you say? So is this graph parallel rigid? We know that if we know the size of, if we know if we know the angles in a triangle, then
it's similarity of triangle.
Right, similar triangles, exactly.
So it is parallel.
So this is parallel rigid, which means that we know the positions up to scale. Okay, good, fine. What about this one, this formation? Is this parallel rigid?
I think that yes.
Yes.
In
Okay.
contrast to the previous case where you knew the distance, because now you have the angles.
Right. Okay. So let's see how. So the first one is determined up to scale. The second one is also determined up to scale, the second triangle, but because they have this shared edge, the scale is determined by, so once I determine the scale for the first triangle, I determine the scale for the second one. Okay, so because of this, all this thing can be scaled globally, but each triangle cannot be scaled differently than the other triangle. Okay, and so this is a parallel rigid structure. What about this one? Is it parallel rigid? So think about it. Each triangle is determined up to scale. Can they scale one triangle and scale differently the other triangle?
Yes.
Yes, so it's not parallel rigid. Okay, so this red is an example of a different position that is not trivially related to the first position. What about this quadrangle? Parallel or not parallel rigid?
Parallel.
Not parallel. Okay, look at this. I can extend, so I know the directions. I don't know the distances. I can extend each of them. Okay, and this side is parallel to this one. This side is parallel to this one. Okay, and so we got a different quadrangle. Sorry. This is just a scale factor.
But Ronan, isn't it? It's just a scale. Yeah.
No, my drawing is bad. My drawing is bad. I can continue here and take this side. Okay, let me try to. No, I won't be able to do it on the spot. Okay, I can essentially extend this in one direction, right? My drawing is bad. I can, for example, take this side, just extend it, this side, the bottom here, extend it, and then take a parallel line here, okay? And this is not a uniform scale, okay? So this is not parallel rigid. My drawing is bad. Let's see how we use the theorem to prove this. Okay, so we're talking now. These examples are in 2D. Okay, so we need a subset of the edges such that the number of edges is 2, the number of vertices minus 3. Okay.
So in the last example,
let's see.
We need 5.
Let's see the examples one by one. Okay. So a triangle is parallel rigid. Simply, you see that 2 times 3 minus 3 is 3. Okay. At least the first part of the theorem is satisfied, and you can verify the second part. Okay, 2 triangles that share a vertex, this example, are not parallel rigid. Okay, 6 is less than 2 times 5 minus 3, which is 7, right? Now, if we look at this last example, okay, it's not parallel rigid because 4 is less than 2 times 4 minus 3, which is 5. Right? But if we add one more edge, then we get this example, and then it's parallel rigid. Okay? Nadav, you still want to ask a question?
No, thanks.
Okay, let's see examples in 3D. Okay, a triangle is parallel rigid. Okay, 3 times 3. Okay, maybe I should say first. Now we can use every edge twice if we want. We can use it either once or twice. Okay, and the set should be 3 times v minus 4. Okay, so a triangle is parallel rigid. 3 times 3 minus 4 is more than 6. Right? And so I can choose, so this is 9 minus 4, that's 5, sorry. 6 is more than 5, right? So I can use 2 edges for every edge here, except for 1. Okay, 2 here, and 1 here. And I get a subset that satisfies this equation. Okay? 2 triangles that share a vertex are not parallel rigid. Why? So first, see that 12, that's 2 times the number of edges, is more than 3 times 5 minus 4. Okay, we have 5 edges. So 3 times 5 minus 4 is 11, right? Okay, so I can use every edge twice except for one of the edges. Okay. However, so one of the triangles has only 5 edges, and that would violate the conditions that, let me see. Sorry. So one of the triangles will have all the edges twice. Okay, that means 6. Right? Because we need 11 overall for the first condition. Okay, and 6 is more than 3 times 3 minus 4, which is the condition for the subset. Okay, we need this condition to be always less than. Okay, I don't know if you remember, we're close to the break, so I don't want to go back to that. But the second condition is not satisfied, and that means that this is not a parallel rigid. Finally, and that's maybe a surprise, this quadrangle, it's not really a quadrangle. This formation in 3D, and generically in 3D, which means that it's not coplanar, is parallel rigid. And you can see at least the first condition that the number of edges is 4, so we have 8 here. It is equal to 3 times 4 minus 4. Okay, do you want to try to understand, to try to imagine why this condition, this structure is parallel rigid in 3D? Any idea? How come?
Yeah, you can think of like a plus sign, one over the other or something like that, and you know the distances.
No, you don't know the distances. You
know the directions. Sorry.
Okay. Yeah. Okay, let me try to explain this. These 4 points are in 3D. You can take any 3 points. Let's take this one and this one and this one. They are coplanar, right? These 3 points are also coplanar. Okay, so we have 2 planes here, this plane and this plane. 2 planes intersect in a line. Okay, so the directions of these 2 planes determine the direction of this line. So in fact, even though we didn't have an explicit edge here in the diagonal, the direction of the diagonal is actually known. Okay, and that's why this is parallel rigid. Okay, and that's not true if the 4 points are coplanar. Okay. Okay, so at least you get the impression that this is not a trivial question. Okay, I want to end this part by telling you a simple way to test generically parallel rigidity. Okay, simple algorithm is the following. Given a graph, I can randomly choose endpoints, for example, from a Gaussian distribution. Okay, use them to form this matrix RP. Okay, that's simple. Okay, for every edge, we just produce the corresponding projection matrix. Okay. Next, we form an orthonormal basis for the trivial null space. And the orthonormal space, this orthonormal basis is simply spanned by the P, which is the points, P1 to Pn, okay? And then you take the unit vector E1 to ED and just stack them as we did before. So this 1 cross E1 means that you get this vector that we showed. We have it here. So you just build these vectors. Okay. So this is an explicit construction of the trivial null space. And finally, you compute the smallest eigenvalues of the matrix RP transpose RP plus UU transpose. Okay, so this matrix should be invertible generically if the points are parallel rigid. Okay, so this determined with probability 1 parallel rigidity. Okay, questions?
What was U?
U is the matrix produced by the null space, the basis for the null space. Okay.
How much P we choose?
Oh, say it again.
How many P's are we going to
No,
choose?
so that is determined by your problem. So for example, I apply multi-view structure for motion. I get 200 images. Then P would be 200, the size of P. Okay.
So I'm choosing everything.
I'm choosing a graph of, I have the graph basically. Okay, I don't know yet the solutions, right, to the graph. I don't. So before I start my recovering, solving structure for motion, I can test the graph and see if I should get a unique solution, if the points are, if the cameras are in general position or not. Okay. That's the idea.
Okay.
There are also algorithms to find the largest rigid component, which is useful in this case. In this case, you will throw some images, but we will not get into that. Okay, let's take a break. 10-15, so in 10 minutes.
אפשר לשאול משהו בינתיים?
Okay.
בכללי יותר,
Just pause recording. Yes. Okay. What about the uncalibrated case? So far we said that in the calibrated case, we really need to solve a problem of parallel rigidity, and that was the main subject of the first hour. What happens in the uncalibrated case? It's essentially similar, but we will just look at it very, very briefly. What we need is the following. Given a graph, we need that the number of edges will be equals to 7 times the number of edges in, we need to find a subset of the edges whose size is 7 times the number of edges minus 11 times the number of nodes plus 15. Okay, let's explain where we got this. Okay. So let's see what, sorry, I skipped a little bit ahead, so say it again. Let's define D to be 7e minus 11n plus 15. In the uncalibrated case, a graph is solvable only if this number is greater or equal 0. Okay. And in addition, for any subgraph, D of n prime e prime, so if I take a subgraph with n prime nodes and e prime edges, this function D is less or equal to D of the entire graph. Also, we require G to be 2 connected, which means that if I take out one node, then the graph is still connected. And any vertex has degree at least 2, and no 2 adjacent vertices have degree that equal exactly 2. So these are all conditions. So in this paper that that investigated this, they didn't have like an if and only if statement. So I had to take this from several theorems. But anyway, that these are more or less, I think, more or less all the conditions for a graph to be solvable in the projective case, uncalibrated case. Now, let's explain why we need D of NE to be greater or equal 0. Where does this coming? Where is it coming from? So each edge now, in the uncalibrated case, we have a graph with n nodes, okay, and e edges, and for each edge, we have a fundamental matrix. Okay, a fundamental matrix has 7 degrees of freedom. Why? It's a 3 by 3 matrix, 9 components. It's determined up to scale, so 8 degrees of freedom, and in addition, it is rank 2, so the determinant is 0. Okay, so that gives you 7 degrees of freedom. Okay. A camera matrix is 3 by 4 up to scale, so it has 11 degrees of freedom. Okay. And in addition, a global coordinate frame in P3, so a projective coordinate frame in 3 dimensions, it's a matrix 4 by 4. Okay, so so it has 15 degrees of freedom. It means that if I put 3-dimensional points in the projective space, if I change their coordinates, that would require me to multiply them by a 4 by 4 matrix up to scale. Okay, so a global coordinate frame is determined by 15 degrees of freedom. So from these things, I can tell you that the edges give you 7 equations per edge. Okay, it's supposed to be 7E here. And the number of unknowns are 11 times the number of cameras minus 15. Okay, so this implies that to solve this problem, the solvability problem, or to be able to determine the positions of the camera parameters, we need to have 7E greater than 11N minus 15. Okay. These are some examples of solvable graphs. You can see that triangles are always solvable, and we will get back to that. But there are quite complicated structures that are still solvable. Okay. Questions? Okay, so
yeah, what about the dimension? Okay, here the graph is like you don't try to embed the graph in.
No, so here we really just want to recover the camera matrices. So I mean, you could say that camera matrices are points in 12-dimensional spaces, but 12-dimensional projective spaces, but it's not as simple as saying, you know, we know the orientation and we determine the positions of the cameras. It's more complicated, more abstract. Okay. Okay. In the rest of this class, I will talk about, I will go back to averaging problems. And what we want to do next is to do averaging of fundamentals and essential matrices. So the idea is that we have a collection of images. We produced from them fundamental or essential matrices. We solve the epipolar constraints, depending on whether they are calibrated or not calibrated. Okay, we may have all or a subset of the fundamental or essential matrices. The measurements are noisy, and we want to make them consistent. We want to average these measurements. Okay. And as I said in the beginning of this class, this is work that was done by Yoni, Amnon, and Merav. And the question was, how can we average essential and fundamental matrices? And what's nice about this idea is that if we can do that, we can simultaneously average rotation, translations, and internal parameters in one optimization, unlike LUD. And what we were able to show is the following. First, we provide a complete algebraic characterization of consistency. So when a graph of essential and fundamental matrices are consistent, we will see that. And then we introduced a direct averaging algorithm for such matrices. And in addition, we also treat collinear camera configurations that are problematic, as we will see later. Okay, so let's define a construct that we call an n-view fundamental or essential matrix. Okay, the idea is very simple. Given a graph with fundamental matrices, we build a matrix that is 3n by 3n. Each block is a fundamental matrix. F12 is between image 1 and 2, etc. Okay, the diagonal is 0. F11 is 0. F22 is 0. Okay, and in addition, this matrix is symmetric because Fij transpose is Fji. We will understand this in a minute, why this is true. Okay, and the question is, if the graph is consistent or not consistent, what can we say about the matrix? What conditions over the matrix imply that the graph is consistent? Okay, notice we're talking about consistency, not rigidity. I hope the difference is understood. Yes?
Why is the diagonal is 0 and not identity?
So we will see in a minute why we have 0 there. Okay, so we all know how to build, how essential matrices factor and our fundamental matrices factor, right? Essential matrix EIJ is rotation times translation, right? And the fundamental matrix, you take the essential matrix and multiply by the inverse of the calibration matrix from both sides, right? That's what we learned in Introduction to Computer Vision and here. Okay, but can we relate the essential and fundamental matrices to global coordinate system? We actually saw something in the last class, but that was quite complicated to use. Here is another expression that is simpler and will be very useful. So it turns out that EIJ can be written as Ri, this is the rotation of camera I, okay, times Ti minus Tj. Ti is the position of camera I in global coordinate system, okay, times Rj, okay? And of course, Fij, I will need to multiply by the calibration matrices, so I can write here R bar I, which is just Ri times Ki inverse, okay? So this is an expression that we actually came up with a few years ago. The idea is very, very simple. I won't prove it, but the idea is very simple. You have n cameras, okay? N images, n cameras. You apply rotation to all the cameras such that they will be parallel to each other. They will look in the same direction, okay? If you do that, then the difference between the cameras is only translation. Okay, is that clear? And it will be exactly the difference between the locations of the cameras. Okay, so this is this equation exactly reflects that. Okay, you apply a global rotation to camera to image J, and the global rotation to image I in the other side. Okay, now both cameras are parallel to each other, and so the difference between them is Ti minus Tj. Okay, that would be the essential matrix. Okay, so and you can see also that if now I'll write Eij in the coordinate system of camera J, for example. Okay, what will happen then? Rj is the identity, right? Because we are in the coordinate system of camera J. Tj is 0, again, for the same reason. And so Eij will be Ri transpose Ti in the coordinate system of camera J. So it's exactly Rij times Tij. Okay, so this shows that this expression generalizes over this well-known expression. Okay, and from here you can see that Eii is 0 because Ti minus Ti is 0. Okay, and you can see also that Eij transpose is Eji, because if you transpose this, you will change the order. And remember also that Tj transpose is minus Tj, because it's skew symmetric. Okay, so these give you the conditions that I mentioned before. Okay. Fine. Okay. So now to derive this consistency constraint, we're going to, there is a very nice observation, I think, that really leads to our constraints. Okay, so I'm going to write generically Fij equals Ri transpose Ti minus Tj Rj. And I'm saying generically, both for calibrated essential matrix and uncalibrated fundamental matrix, simply the difference is whether R is a rotation matrix or a general linear transformation. Okay? Okay, so we have that Fij is this expression. Okay, and if I open it, it's Ri transpose Ti Rj, which is written here, minus Ri transpose Tj Rj. Okay, and now let's call this term Aij. Aij is a 3x3 matrix produced by multiplying the first rotation, Ti, the skew symmetric matrix of translation, and Rj. Okay, good. Now I want to convince you that this matrix is also a kind of Aij, but with different, with two differences. First, it's a transpose, and secondly, the subscripts are Ji. Okay, how? Let's see. So if I take this thing and transpose it, okay, I should get Rj transpose, right? So it's Rj transpose minus Tj transpose, that's plus 2 Tj, okay? And Ri, right? You agree with me that this thing transpose is this thing? Okay, and this thing is exactly Aj, right? Just compare, you know, pattern comparison. Okay, so this part and these parts are related, and what I'm going to do next is simply have a big matrix A, 3n by 3n, whose blocks are the Aij, okay? And I'll make it also, that's it, okay? Okay, and I know that if I transpose it, it will contain the AJI transpose also. Okay. Okay, so so as we saw, Fij is Aij plus AJI transpose. Okay, and this means that the matrix F that we saw in the beginning that contains all the Fij's is A plus A transpose. Okay, and moreover, A is rank 3. And the reason is that, remember that Aij, let's go back. Okay, Aij was composed of Ri transpose Ti Rj, so I'm going to use this structure to factor A. And you see that A factors to Ri Ti, this matrix, times Rj. Okay, I'm going over all i's and all j's here. Okay, and I get a 3n by 3 matrix here and a 3 by 3n matrix here. Okay, which means that A is rank 3. And since F is A plus A transpose, it must be of rank at most 6. Okay, and it turns out, and we proved that the rank of F is exactly 6 if the cameras are non-collinear. Okay, I hope this is clear. The last part for understanding that I'll explain at least, that for understanding the consistency is the following. What we showed is that F is equal to A plus A transpose with rank A equals 3 and F is equal 6. The rank of F is 6. I'm claiming that this is equivalent to saying that F will have 3 positive and 3 negative eigenvalues. Okay, this is shown here, but let me skip because it's just technical and I think we're a little bit short of time. Okay, so from all of this, we get the following theorems. Okay, so an n-view fundamental matrix, so a graph of fundamental matrix, is consistent, okay, under the following conditions. So first, what is an n-view fundamental matrix? Is a 3n by 3n matrix F with the condition that F is equal F transpose, Fij is 0, and the rank of every block is 2, okay, which basically makes this a fundamental matrix. Okay, so such a matrix, an n-view fundamental matrix, is consistent if and only if the rank is F, the rank is 6, sorry. F has 3 positive and 3 negative eigenvalues. And in addition, we need that every column block, 3n by 3, should be full rank, should be rank 3. Okay. If F is consistent, then the camera matrix are determined uniquely. Okay, I can use F to determine all the cameras. Is this clear? So these are algebraic conditions that tell you that F is consistent. Okay, and now then the next thing is that given measurements, given F's that are inconsistent, we will use averaging to make them consistent and therefore determine the camera matrices. What about essential matrices? So an n-view essential matrix is essentially exactly like an n-view fundamental matrix, 3n by 3n. The only difference is that for every block Eij, the two singular values that are non-zero should be equal. Okay, that makes every block an essential matrix, and so this 3n by 3n is an n-view essential matrix. Okay, and the conditions for consistency, so E is consistent in addition to the conditions for the F to be consistent. We have that the eigenvalues are equal in absolute value. So lambda 1 equals minus lambda 6. They come in pairs. Lambda 2 equals minus lambda 5. And lambda 3 equals minus lambda 4. Okay. And yes?
Why is that?
Okay, so that comes from this condition. So I didn't prove it, of course. We said in the case of fundamental matrices, we have 3 positive and 3 negative eigenvalues. And it turns out that in the calibrated case, the 3 positive ones are exactly equal to the 3 negative ones up to sign. Okay. In addition, there is some rotation constraint on the eigenvalue, on the eigenvectors. Okay, the eigenvectors, if you sum them up, the eigenvectors for the positive and the negative eigenvalue, you will get block rotations. So this is a more complicated condition. Okay, but these are if and if conditions, so if and only if, sorry. So these are sufficient and necessary constraints, and we can use them in optimization. Okay, so how can we use these conditions to average fundamental matrices? We want, in an averaging algorithm, to handle missing fundamentals, erroneous ones, and even maybe outliers. Okay. The problem is that first enforcing rank constraints is itself difficult, but also that every fundamental matrix is only given up to scale, and we don't know the consistent set of scales. So one possibility which we tried in a previous paper is to solve for both scales and cameras. And this leads to a non-convex optimization that required a good initial guess. And that was not so good. So we wanted to improve over that. So you can see here just the formulation. Given your fundamental matrices Fij, you want to find consistent set of Fijs up to scale lambda ij. So the minimization is over Fij and lambda ij, okay, such that F is decomposes to A plus A transpose, the rank of A is 3, and Fii is 0. That was the first attempt that we did to do averaging. And as I said, it wasn't so good. We really had to use a good initial solution.
How do you choose the initialization here?
We actually used LUD, which was really bad in some sense. Okay. So the real problem here is overcoming these scale factors, the problem with scale factors. So, so then we came up with an idea how to solve the problem of scale factors. The idea is the following. Let's see. So the question is how many scale factors we need to find for n views. Okay, so we have n images. Okay, and every fundamental matrix Fij can be scaled. We don't know the scale factor. We solved an homogeneous problem to solve for the fundamental matrix. So essentially, we can have up to n choose 2 scale factors that we need to solve for, right? That's the number of the maximal number of fundamental matrices that we can have. However, in the projective case, the cameras are determined only up to a scale themselves. Now, cameras, we have n cameras, right? Which means that we really need only to determine n choose 2 minus n scale factors. The rest can be used to scale the cameras. Okay? And now, interestingly, if n is 3, then n choose 2 minus n is 0, which means that for 3 images, if we take 3 images and we have all 3 fundamental matrices, the 3-view fundamental matrix will be consistent even if we don't scale the fundamental matrices, if we don't know the scales, because all this scaling the matrices will be equivalent to scaling the cameras in this case, which is fine in projective spaces. Okay? Therefore, we do not need to solve for 3 views, we do not need to solve for scales. Now, remember, we talked about solvability. A graph like this is solvable. So these are 3 views, 3 nodes, 2 triangles connected by an edge, while a graph like this is not solvable, right? Or, you know, in the calibrated case, this is not parallel rigid, this is parallel rigid. So the idea is the following: given n views, what we will do is we will create a triangle cover of the graph, okay, such that every neighboring 2 triangles will share an edge. Okay, this is a cover of the graph. And now the idea is the following: if I can make sure that this triangle is consistent, the fundamental matrices over this triangle are consistent. And if I can tell you that the fundamental matrices over this triangle are consistent, then I can make all of this structure consistent without knowing the scale factors. Okay. Essentially, this triangle will determine the camera matrices up to a global transformation. The global transformation is a 4x4 projective transformation, right? A 4x4 matrix up to scale. This one will create the projective cameras up to this 15 degrees of freedom. And I can move them such that they will share the same coordinate. I can solve and extend the cameras and such that, and this is because this structure is unique. Okay, so that's the idea. This triangular cover in this matrix, okay, so if we have a 3n by 3n fundamental matrix, okay, a triangle is simply a 9 by 9 submatrix. The blocks don't have to be consecutive, so I mean, here I plot them as if they are neighboring, but you can take any triplets of blocks and take a 9 by 9 submatrix with 3 by 3 blocks for this triangle. So this is a triangle, okay? And let's say this is a second triangle. If they share an edge, that means they share a 2 by 2 block. Okay, so I need a structure like this that will cover all the nodes in the graph. Okay. And this is the next, this is the optimization that we want to solve. Okay. So given measured fundamental matrices, I take them over each triangle. Okay. And I just want the difference here between the fundamental matrices that I predict to be small. Okay. Under the constraints that F is equal to F transpose, FII equals 0. That makes it an n-views fundamental matrix. And the rank of F for every triangle is 6. Okay, so notice, yes?
As I understood, we have this formulation for every 9 by 9 subnode.
In the triangle cover. Okay. Not every 9 by 9 submatrix, but every 9 by 9 that correspond to a triangle in the triangle cover. Okay.
And there is no contradiction between one solution and another one.
Exactly. So the global matrix F that I produce here will not have rank 6. But if I put the correct scale factors, it will have rank 6. But I don't solve for the scale factors. Every 9 by 9 here will have rank 6, but they will still be compatible because they form a rigid structure. Okay. And what is really nice about this formulation is that we can solve it with ADMM and we don't need initialization at all. We simply initialize by these matrices that we produce, that we measured. So no external method for initialization. Okay. So I wanted to basically just say a few words about ADMM, alternate direction method of multipliers. You didn't study it here, right, in this course?
No.
Okay, some of you maybe learned it in an optimization class before. So I'll make it very brief. The idea is that given an optimization problem, you can try to break it into different steps that will be simpler to solve. Okay, so suppose I want to solve a problem of the form fx plus gx. Okay, I somehow just take my optimization and treat it as a summation of two terms, which I call f and g. Okay. What I will do is I will produce a new copy of x that I will denote y. And I will try to solve minimize f of x plus g of y subject to x equals y. Okay, that doesn't seem like much of a difference. But now what I'll do is I'll treat this as a constrained optimization and try to solve, and I'll try to minimize fx plus gy plus some Lagrange term, which is coefficient times y minus x plus some lambda, which I'm trying to maximize here. Okay, and it turns out that this can be solved in 3 steps. First, I minimize with respect to x. Then I minimize with respect to y. So in the first step, I don't look at g of y. In the second step, I don't look at f of x. And finally, I make an update of gamma, and the update is just an update. You don't need to minimize anything. Okay, so that's the basic form of ADMM.
What about the last step? I'm missing something because you try to maximize with lambda. So why not taking it to be just like infinity or something? Like,
It's like
what's the V over 2? It's V over 2?
V is just a parameter which you determine in the beginning, and it remains constant, basically.
So to maximize this expression, why not just exploding, like taking and exploding a lambda or something?
Yeah. The thing is that you're trying to minimize. I'm not sure I have an answer for you now. Yeah, why wouldn't that make X and Y very different from one another, right? I will have to look into this. I don't remember. Okay, so what we want to do is to minimize this problem, minimize the difference between our measured fundamental matrices and the consistent recovered fundamental matrices over the triangles, subject to the constraint that the rank over each triangle is 6 and is linear constraint. Okay. And what we will do is, I need a moment to remind myself. Okay, so what we will do, basically, corresponding to what I showed before, is to write this Lagrangian. We sum. So here you have the summation over all the triangles, plus this difference between this new matrix B, BK, and F, okay, and this gamma. And what we want is the rank of B to be 6. So B plays the role of Y in the previous thing. So B is a copy of F. Okay, we want B to be rank 6, and we want F to be close to our measurements. Okay, and we solve this iteratively in 3 steps. We minimize with respect to F. So we solve this, and we ignore the rank constraint. Okay, and this is just a least squares problem. Okay, then we minimize with respect to B. Okay, so we ignore this part. Here it's least squares, but we have a rank constraint. Okay, and essentially since we look at triangles, these are full 9 by 9 matrices, and so we can use SVD to solve this problem. So we enforce rank 6 by SVD. Okay, and then we update gamma and we repeat iteratively.
Well, then I have a question.
Yes.
I know that BK is 9 by 9. Okay, it means that it can have a rank till 9. Okay.
Exactly.
But what happens if the initial rank is lower than 6? Do I need to add something to this singular values?
It's a good question, but it shouldn't happen. Remember that the fundamental matrices are all rank 2, and I think that so it could happen if you somehow have, for example, collinear cameras. What will happen here is that this condition will be satisfied, and you will so it will work. Maybe not too good because your structure is degenerate, but it doesn't affect the optimization itself. So we don't enforce exactly rank 6. We enforce rank smaller or equal 6.
So yeah, this is also my question, like how we enforce the rank, how we make sure that, how do we use the SVD to ensure that? Okay,
so SVD, so basically least squares with, so if you want to solve a least square with rank constraint, SVD really solves this problem. Okay, because that's right. SVD finds the nearest in L2 matrix that has rank 6 or any determined rank, but really up to rank 6. Okay. Now, generically, that would happen unless you have triangles that are collinear, and really in the algorithm we actually make sure that we don't have collinear triangles.
Because you mean that like we can drop the singular values and just zero them?
Yes. Yes. We can check the singular values.
Okay, so the method is just zero the unnecessary
Exactly.
singular values, and okay, yeah, I see. Thanks.
Right.
I have also more question. One more question.
Yes.
How do we do what unknown here is? The unknown is with the hat or without the hat?
Without the hat. The hat are measurements.
So the measurement need to be also initialized in some way.
No, the measure, right. So you take, so here is the pipeline. That's exactly, so let's see the pipeline. Okay. The input, so really we start with images, but what we do is we take pairs of images and estimate the fundamental matrices. That gives you F hats. Okay. In addition, we produce point tracks that we will use in the end in the bundle adjustment step. Okay. So for our algorithm, really, we have the graph with the fundamental matrices. Okay, F hat. Okay, we take this graph and first produce a triplet cover. Okay. Sorry, the mouse stopped moving. So we construct a triplet cover. Okay. We form an n-view fundamental matrix, F hat actually. Okay. Next, we use ADMM to make F cover consistent, that we solve the previous optimization from the last slide. Okay. Then we use the recovered F to form the camera matrices. Okay. Given the camera matrices, we triangulate the points from the point tracks. Okay. And we refine the solution using bundle adjustment. Okay.
Okay, so as I understood, we do, all this is for triplets.
No, so the optimization is for all the n images. You sum over all triplets. Okay, you minimize over the sum. So you optimize over the entire graph. Okay.
But
every term is a triplet.
So does it mean that this method is like better when we have images that are like somehow similar, like we saw in the previous lectures, estimations of I don't know, like a Rome or like a scenes or like maybe we don't. It could be difficult to estimate the fundamental matrices if we don't have point matches.
You can see
Like,
here the instruction. It will be, you can do this step. So up to the bundle adjustment, you can do everything without point matches if you have fundamental matrices somehow measured in a different way. Okay, so for example, if I run a deep networks that give me fundamental matrices, and it doesn't give me matches, I can run all steps up to step 5, so up to step 4 really, without and get the cameras without point matches. Okay.
Okay, so our method, this current method, just like enforce guarantee the consistency.
Yes.
Right.
And by that allows you to recover the cameras. Okay.
Thanks.
Well, then I have two questions. First question is, when we estimate the fundamental matrices in the first stage, some images will not be covered by, you cannot calculate a transformation matrix between them.
Yes, that
So
could be. So the graph will not be complete, of course, and you don't need it to be complete.
So in the end view matrix, you will have zeros.
Missing data, right? It will have missing data, and
Missing data, it means zero, so it will be none.
we ignore them. I mean,
So we don't select triangles with unknown data.
Exactly.
And this is follow to my second question. Is there optimal way to select my triplets?
So we didn't do it. I mean, we selected it by some heuristic. It's not optimal. I mean, you could try to do this over all triplets, but that would be just more expensive in terms of runtime. Okay.
Yeah.
There is no problem of redundancy here. In the end, everything will be consistent. Let me skip here. We get very good results. You can see this here. Let me skip the optimization of the Euclidean case. And let's see some reconstructions of the Notre Dame chapel in Paris. The cameras are the green things here. And here is another Notre Dame in Montreal.
How much time it took to calculate it?
How much time did it take?
About 10 minutes, I think.
10 minutes on 1 million GPUs. But no, I'm kidding.
No, but
how do you
taking the correspondences is longer. I did not include it in my calculation.
How do you measure the result? So how do you know that this one is better than?
Okay, so the way you can measure in different ways. For example, how you have ground truth flotation and translation. In this case, usually they are computed by some other methods, so they are not really ground truth, but unfortunately they don't, I mean, laser measurements, they are only on very small data sets. Another thing is reprojection errors. So you can use those measurements. Okay, we're a little bit behind. So I just want to say that there is a problem though with collinear cameras. And the reason is that measurements between pairs of images don't tell you enough, don't give you all the information that you need to solve for collinear cameras. Okay, so you don't know, you can't tell from just pairwise measurements the distance between one camera to the other relative to the distance between one camera and the third one. Okay, so how far you walk along a line, you can't tell from correspondences between pairs of images. And that means that you will not be able to say that also from fundamental matrices. You have to have correspondences between 3 images for that. Okay, so it turns out you can still use our method also for collinear cameras. And the idea is very simple. If I have a correspondence between 3 images, so think about this point, for example, if you did triangulate it, it would give you some 3-dimensional point here. Okay. Now what you can do is to put a virtual camera in the position of this point. Okay. If this point is not collinear with your 3 cameras, that will create a virtual camera that is non-collinear with your cameras, and you can use it to compute the fundamental or essential matrix between the virtual camera and the 3 cameras here. And then once you do that, you can put it also in your NView fundamental or essential matrix and use our method to solve for the problem. Okay, so this way you can produce virtual cameras that are non-collinear and solve for them. Notice that we had to use correspondence between 3 images. That's how we managed to get this additional information. And here you can see an experiment where with a car moving along a line. Let's see. Okay. Our reconstruction is the red one, I think, right? Or the blue one. Okay. I should write it on the red.
What are the points?
Okay, so the points are just 3-dimensional points from the scene. Okay, and what you see here is the ground truth should be green.
The ground truth is green.
The red
Ours is red, and the competing method is blue.
Yes, I think it's LUD.
Yes, it's LUD.
Okay.
What are we seeing now is the state of the art, like the competing method is
for averaging techniques. Yes, so incremental technique, you know, Colmap is still slightly better, I think. But in averaging technique, that's the state of the art.
Can you explain again how do you calculate the virtual camera and the relation and the fundamental matrix to from the each picture to the?
I didn't explain this, and I didn't include this in here. I just told you that it's possible. Yoni, you remember? I don't remember offhand.
Sorry, I missed the question. What was the question?
How to compute the fundamental matrix or essential matrix for the virtual camera. I think
we have a formula from the
formula, but I don't know.
Yes, from the point and from the point match, and we set arbitrary rotation for the virtual camera.
Yeah, it's just the formula. I don't know how to explain it. Okay, so we're out of time. To conclude, we talked about rigidity constraints and how we can tell if a graph should be solvable in generic positions. And we talked about averaging techniques, and in particular, how to average fundamental and essential matrices. I guess that's it for today. Any more questions?
Yes, I have a question, but maybe offline, like at the end.
Okay. Anything else? Okay, if not, I'll stop.